In the previous part of kinetic, we define rate, instantaneous rate of the reaction, average rate of the reaction, the relation between the instantaneous rate and the rate of the reaction according to the stoichiometry. Then we talked about the factors that affect the rate of the reaction. The factors are the temperature, the initial concentration of the reactants, adding a catalyst, the surface area of the reactant, and the pressure in case of gas. The objective of this part is to find a relation that relates the rate of the reaction to the temperature and the concentration of the reaction of the reactants. So we will talk about the rate law expression. Suppose you have a reaction AA plus BB that give CC plus DD. The rate of the reaction can be expressed by R equal K A concentration of A to the power M times concentration of B to the power N. This is called the rate law expression, and this equation can be applied at any time t of the reaction. If we look to this rate law, we observe that the rate of the reaction is directly related to the concentration of A and directly related to the concentration of B. As the concentration of the reactants increase, the rate of the reaction increase. This is the first factor of concentration. Also, the rate of the reaction is related to the temperature of the reaction, and we use what we call K, which is indication about the temperature of the reaction. So as K increase, the rate of the reaction increase. So in this equation, we relate the rate of the reaction to the temperature included in K and to the concentrations of the reactants A and B. What is M and N? For some reactions, you did an experiment starting at concentration of A equal A1. So you can obtain the rate of the reaction for this concentration. Suppose you repeat the experiment and initially you double the concentration of A. Also, the rate of the reaction will increase. But the change of the concentration of A on the rate is not in general the same as the change of the concentration of B on the rate of the reaction. For this reason, we use the terms M and N to indicate what is the effect of the change of the concentration of A and B on the rate of the reaction. So K is a function of the temperature. And since we did the reaction in one experiment at T equal constant, so for T known, K is constant and is called the rate constant. K depends on the nature of this reaction, and it depends on the temperature of the reaction. For two different reactions, we have in general different value of K. For two experiments of the same reaction realized at the same temperature, K is the same. M is the partial order of the reaction with respect to A, or in other words, this is the effect of the change of the concentration of A on the rate of the reaction. N is the partial order of the reaction with respect to B, or the effect of the change of concentration of B on the rate of the reaction. And M plus N is the global or the total order of the reaction. The objective of this part, I will give you a reaction and I will ask to find the rate law expression. In other words, is to find what is K for this reaction and what are the partial orders M and N, and you can deduce what is the global order of the reaction M plus N. As a conclusion also, pay attention that for the same reaction, M and N are constant, are the same. So the temperature, if you change the temperature and the concentrations of a reaction, you obtain the same M and N. Suppose I realize the previous reaction at concentration A1 initially, B1 initially of B at T equal 25. I repeat this experiment, independent experiment, but I start at concentration, initial concentration of A, A2, initial concentration of B, B2, and suppose I change the temperature. So in these two experiments, I change the temperature and I change the concentrations of the initial reactant. But since the reaction, the nature of the reaction is the same, so M and N are the same in the two experiments. The rate, the concentration of A and that of B should be used at the same time in the rate law expression. I can write R at 5 minutes, K is independent of time, K is constant, times A at 5 minutes to the power M, times B at 5 minutes to the power N. And I can write also R at 50 minutes equal K, A at 50 minutes to the power M, B at 50 minutes to the power N. So pay attention in the same rate law expression, R, A, and B should be used at the same time T. The partial orders may be integer numbers, M and N, or fractions. In your curriculum this year, M and N are equal in most cases 0, 1, or 2. How to determine the rate law expression for a certain reaction? Or in other words, what is the importance to find the rate law expression? When we find the rate law expression, that means you find K, you find M, and you find N. So we know R equal KAM to the power N. Suppose they ask us, start this reaction with a concentration of A equal a certain number with a concentration of B equal given number. It's not necessary to repeat this reaction in the given conditions in the lab in order to find the rate of the reaction. If you know the rate law expression without doing the experiment, you know the concentration of A, you know the concentration of B, you know M and N, and you know K, so you can determine the rate of the reaction directly. The rate law expression is determined experimentally one time. You did the experiment one time to find the rate law expression. and there is no necessary relationship between the form of the rate law expression and the form of the balanced chemical equation. For example, the transformation of CH3CN to CH3NC. The rate of the reaction found experimentally is equal to K times the concentration of CH3CN to the power 1. So the partial order in this reaction is equal to the stoichiometric coefficient of CH3CN. In the second reaction, we observe that the partial order of CH3CHO is 3/2, and the stoichiometry of CH3CHO is 1. In the decomposition of N2O5 to NO2 and O2, the partial order of N2O5 is 1, and the stoichiometry of N2O5 in the reaction is equal to 2. So there is no necessary relationship between the form of the rate law or the partial orders and the stoichiometry of the reactants. The reaction order is always defined in terms of the reactants and not the product concentration. R of the first reaction is given according to CH3CN and never according to CH3NC. In the decomposition of N2O5, the rate law expression should be expressed as a function of N2O5 only and not as a function of NO2 and O2. This is an important point to define the rate law expression according to the reactants only. The value of K is temperature dependent, but never depend on the value of the concentration. So for the same reaction realized at different experiments, if you did these experiments at different concentrations, the value of K in the four experiments is the same if the temperature of these reactions is the same. So K is only temperature dependent of the reaction. Example 7.2. The rate equation for the reaction of NO with ozone is R equal K times concentration NO times concentration O3. So the partial order of the reaction with respect to NO is equal to 1. The partial order of the reaction with respect to ozone is equal to 1. And the global order of the reaction is equal 1 plus 1 equal 2. If the rate is 6.6 10 minus 5 molar per second, when NO equal 1 10 minus 6 and O3 3 10 minus 6, calculate the rate constant. So first of all, we have to write the rate law expression given R equal K NO1 O3 1. This expression can be applied at any time of the same experiment of the reaction. We could not use NO from experiment 1 and O3 from experiment 2 to define the rate law expression. R equal K NO times NO3 at the same time for the same reaction, for the same experiment. So this relation can be applied at any time t. One of these times is the time given in the data. So K equal rate divided by NO1 O3 1. The rate and the concentrations are given at the same instant. We put the values and we obtain K equal 2.2 times 10 to the power 7 molar minus 1 second minus 1. Pay attention to make the difference between the equilibrium constant and the rate constant. The equilibrium constant is capital K and is obtained from the thermodynamic data delta G0. The equilibrium constant capital K is an indication about the advancement of the reaction. So capital K is related to the yield of the reaction. Or capital K, the equilibrium constant, is an indication about this reaction, if this reaction is limited, advanced, or complete. The rate constant is noted small k, and the rate constant is obtained from the rate law expression, and the rate constant is an indication about the rate of the reaction at a certain given temperature. Capital K, the equilibrium constant, is unitless, but small k has unit. The rate constant, when you write the rate constant, you have to give the units, since the unit is a strong or important indication in the determination of the order of the reaction. Determination of the partial order of the reaction, and therefore determination of the global order of the reaction. To find the global order M plus N of a reaction, several methods can be used. The choice of the method depends on the type of the data given. This is the same strategy used, for example, when we calculate delta H of the reaction. We said that delta H of the reaction can be obtained by 4 methods. The method we choose depends on the thermodynamic data given. By the same analogy, when you determine the order of the reaction, you have several methods. The choice of the method depends on the type of the data given. We have direct methods 1, 2, and 3, and we have indirect methods. Indirect, we have to correct, this is indirect methods, method 4 and 5. What is the difference between method 1, 2, and 3, method 4, and 5? In method 1, 2, and 3, we obtain M, we obtain N, then we deduce directly M plus N. So we obtain the partial orders of the reaction, then we deduce the global order of the reaction. Method 1 is the log plot, method 2 the ratio technique, and method 3 is the integrated rate law. We pass to the indirect methods, method 4 and method 5. In the indirect method, we could not know M and N. We could not know the partial orders of the reaction. We obtain directly M plus N, so we obtain directly the global order of the reaction. If they ask us to calculate the partial orders, that means we have to use method 1, 2, or 3. If they ask to calculate the global order of the reaction, we can use 1, 2, 3, 4, and 5. But pay attention, method 4 and 5 could not generate the partial orders of the reactions. I will explain the method number 1, which is the log plot. The question is, consider the following reaction, AA plus BB, that gives CC plus DD. Find the rate law expression for this reaction. The rate law expression is R equal K, concentration of the reactant A to the power M times B to the power N. To find the expression, I have to find K, M, and N. The rate law expression, as described previously, can be obtained experimentally, so can be obtained in the lab work. To find M, I will go to the lab and do the following procedure. Make an experiment where the concentration of B is maintained constant in course of the reaction and the concentration of A change with time. I have to go to the lab. I will take a certain amount of A, another amount of B. I will mix in order to do the experiment, but pay attention, I have a condition. Choose A and B in such a way that the concentration of B that will decrease with time, since B is a reactant, but the concentration of B is practically constant, and that of A change with time. So what to do? If I make the experiment with initial concentration of A negligible with respect to B, suppose B equal 100 and A equal 1. So A will decrease from 1, 0.9, 0.8, 0.7, 0.6, 0.5 till 0. And B will also change from 100, 99.9, 99.8, 99.5, 99.4, 99. So at the end of the reaction, B is equal to 99%. Okay? So B is practically constant. The decrease of B is negligible, but the decrease of A is a certain value. So in this case, if you start with high amount of B with respect to A, A0 will change with time, but the concentration of B will be practically constant as a function of time. Therefore, you will do as in grade 12. You will calculate the concentration of A as a function of time, and you will draw the curve variation A is equal Ft. If you draw, for example, the variation of B as a function of time, you will obtain practically a straight line, since the concentration of B is practically constant. From any kinetic experiment, you obtain a set of values. For any time t, you can calculate AT. BT, you can calculate RA at T, RB at T, and the rate of the reaction at T, as in grade 12. For example, at time T, you can know AT from the stoichiometry of the reaction. You can know BT from the stoichiometry of the reaction, from the stoichiometric calculations. How to find the rate of A at time T? You make a tangent at time T to the curve. The negative slope of the tangent, since this is instantaneous rate of disappearance, so the negative slope of the tangent is the rate of A at time T. In the curve of B, you make the same method. You obtain the rate of the reaction of B, or if you know RA at T, you can deduce RB at T, and you can deduce the rate of the reaction of T at T. So in any experiment, you have a set of data, T, the concentration of A at T, the concentration of B at T, RA at T, the instantaneous rate of disappearance of A, RB at T, and you have the rate of the reaction at time T. Since K is constant, and practically the concentration of B is constant and n is known as a constant value, so k b to the power n is constant. I can transform this relation from r equal kam b to the power n to r equal k prime a to the power m. As I said, the RA is determined from the curve at any instant, and you can deduce the rate of the reaction at any instant. So R equal K prime A M. At time t, you have A and you have R, and R is deduced from RA. At time t equal T2, you have A, you have R. At time equal A3, you have the concentration of A and you have the rate of the reaction R. So you obtain a table of three columns. The first column is the time t. The second column is the concentration of A as a function of the time. And the third column is the rate of the reaction as a function of time. So R equal K prime A to the power M. To remember, we have the concentration of A at different times and the rate of the reaction at different times. So ln R equal ln K prime plus M ln A. This is the equation of a straight line. Ln R equal 1, ln A equal X, and ln K prime equal B. So Y equal A X plus B. This is the equation of a straight line. So we draw ln R as a function of ln A. We should obtain a straight line. The slope of the line is equal to M. And by this experimental method, we find the partial order M. So by the same method, we repeat another experiment. In the first experiment, we took A0, the concentration of A0 negligible with respect to B0. So we repeat another experiment. We take B0 negligible with respect to A0, and by the same method, we find N. So now how to find K? K equal the rate of the reaction divided by the concentration of T to the power M, concentration to B to the power N. So in the set of the experiments, in the set of the data obtained in experiment 1, you have set T, AT, BT, RAT, RBT, and the rate of the reaction at T. In the experiment 2, you obtain a set of data T, A, B, RA, RB, and R of the reaction. You can use one of these sets in experiment 1 or in experiment 2 to find the value of K.